Hello, this is Brian Schadrie. I'm a senior mechanical engineer at Global Finishing. And
I'm Andrew Marum. I'm also a senior mechanical engineer. I was on the lighting one a few weeks ago, and I'm here to help Brian out with some energy savings discussion.
So basically with paint booths, there's a lot of different costs involved with them. We have the initial investment, which includes the purchase price, the installation costs, interest and depreciation. There's also the regulatory costs for permitting the booths as far as emissions is concerned. Further on, once the booth is installed and so forth and the users using it, there's the maintenance costs. So there's the filters, there's the filter disposal, there's motors and belts, lamp replacement, those types of maintenance items. And then the last item is the operational costs, and that's what we'll be talking about today.
A lot of the upfront costs, so a lot of the to meet code, to meet the regulations, the overall design of the booth. There's not a whole lot we can cut out, but once we get to the operational side of things, there's a lot of things we can do here at Global to help out, and a lot of things you need to consider to maybe get the most for your, the biggest bang for your buck as far as operating your booth. So.
Right. So in regards to operational costs, there's two main energy users, and that's the electricity and the gas heat. That's typically used for the heating side of the paint booth. So as far as the electricity is concerned, we have motors that drive the exhaust fans, the makeup air systems. There's also lighting, and and some booths can use electric heat as well. But then on the heating side, the biggest consumer is natural gas. These charts illustrate the difference in heating and electric energy based on the location. So in Eau Claire, a paint booth would typically use about 20% of its energy use would be for electricity, 80% for heating. Versus Dallas, Texas, it almost does a flip-flop where electricity is 60% of the cost of energy and heating is 40%. And this is primarily due to climate, because Dallas is a warmer climate than Eau Claire. So what we want to talk about then is what are means and methods of how we can save energy. And maybe you probably recall growing up that one of the biggest thing that we've learned is to shut the lights off when we're gone, right? Or we leave the room. So same scenario with paint booths. Don't have the paint booths operating when it's not actively being used. And there's some strategies that can be used to accommodate using minimal energy for that. So we have strategies like turning down the speed of the fans if you're not actively spraying. We call that an economy mode. So basically, if a painter's in a paint booth spraying and has accomplished his job at the time, he may set the gun down, and he could set it on a switch, for instance, and that switch would be monitored by the system and would automatically disengage or automatically engage this economy mode, which would basically slow down the speed of the system fans to half.
Sure. And so if you think about the general operation of a booth and you look at the two graphs here, obviously up north you're going to be burning a lot more natural gas because your primary goal is to get up the temperature in the winter months or the colder temperatures, right? A paint booth you're probably operating in the 70 to 75 degree range most of the time. So here you're burning natural gas. Here you're running an electric air conditioning unit or something similar if you're trying to cool down the booth. So what you're doing is you're bringing in air from outside, you're tempering it for use in the booth, and then you're exhausting it out the stack. So all that tempering you did, you're pushing that air through the booth and you're just exhausting all that energy back out into the environment. So what Brian's talking about as far as slowing down the fans, essentially you exhaust less of that energy that you've just used, and so you save by being able to turn down your inputs up front, whether that be natural gas or electricity to cool or heat the air.
Yeah, yep, exactly. And And by the way, when, as far as from an electric standpoint on motors and so forth, if I'm driving a 10 horsepower motor during paint mode and now I have an opportunity where I can slow that speed down because of economy mode kicks in and the painter's not actively spraying at that moment, that booth could go down to half speed. Well, what that does from an electricity standpoint is that cuts your electric cost by 8 times. The other strategies we have in our systems are we monitor the filter loading within the paint booth. And what that does is we're able to maintain a consistent velocity through the booth during the lifespan of the filter. So that basically lets us operate the fan just as fast as it needs to throughout the life. So we're not spending extra money up front by running this fan where we're 125% of the rated speed of the system versus just moving enough air all the time so that we're saving energy. And
yeah, it's the same premise, trying to find that optimal operational point where you get the right airflow for your process. You try to dial it in right there, and you want it to stay there. You don't want to have to increase the flow as the filters, or have a higher flow, so when the filter's loaded it drops. You want to keep it constant the whole time. And whatever that minimum amount of airflow you need to operate correctly in your process is, that's where you want to be, because that's the least amount of air you're pushing out the stack, and the most efficient you're going to be in that booth.
Yeah. So as you know, paint booths do use a lot of energy, and the air movers, the fans, require that ventilation, and therefore it adds up in utility costs as far as gas for heating that air and the motors that drive the air. So, a key element in all of this is to make sure that the booth is designed in an efficient manner where you're not moving any more air than you need to, and there's requirements for specific types of booths. Like for open face booths, for instance, a non-enclosed booth, the code requires 100 feet per minute at the open face. Versus a enclosed booth, there are some other attributes that need to be looked at, specifically the lower flammable limit. The lower flammable limit to make sure the atmosphere's safe for the painter. And the other items involved with that is transfer efficiency of the coating to the product, making sure that the overspray is captured, that you're not that the work area is cleared effectively. So there are things that in enclosed booths that give you more opportunities to possibly save energy.
Yeah, and one more limit we do have is a number of our booths are ETL listed. So if you do go with an ETL listed booth, there are some hard limits on how low we can go for minimum airflow. And to be honest, most of those limits are going to be well below, I think, any process that we've run into, as far as nobody's wanted to go below what we have in our reports. But we do have some wiggle room to go lower on airflow than what our standard airflows are. So it's an option if your process allows it.
So on this chart, these are two components that we use typically one or the other for the economy mode. And basically, it monitors the use of or the process of painting in the paint booth. This is a compressed air switch, so it monitors the compressed air to the paint gun. As soon as that slows down, that would send a signal to the control panel. So then our control panel would then engage the economy mode to slow down fans and the ventilation rate to save energy. This works on the same in the same way, but basically it's a hook, so that the painter hangs his paint gun on there, and when it's hung on there, it's understood that he's not painting, and now it engages again the economy mode.
Right, and you can obviously do an economy mode from the HMI itself, but these two devices that we offer will do it for you automatically. So there's an incorporated timer. You hang it on there after a certain amount of time. I think this is actually pretty instant, isn't it? Once you hang it, it pretty much drops to the economy mode. Mm-hmm. This guy's looking for airflow through typically the spray gun. It's telling you the spray gun isn't operating. So if you stop spraying for X amount of time, it'll automatically scale the fans down, and you'll save energy in those downtimes without having to go to the HMI and remember to push a button.
So when we're we're not painters, but really the thing to look at is, from an end user perspective, is take a real close look at your process to understand what are the what percent of time is the booth operating that it's not being actively sprayed in. And you can, from a look at that process, you can take a look, we can figure out what kind of savings could be had by incorporating a system like this. So there's inputs into this that we need to understand as far as your process in order to allow you to understand the total savings that can be had by these different systems. So what we with the economy mode, for instance, maybe in a system where there's we can assume maybe 30% of the time in the paint mode that it may not be needed, that economy could be used 30% of the time. Well, that realizes a savings over a year of maybe 35 to 45% to the bottom line of someone's operation. So the economy mode, if incorporated and can be used in your process, is a good way to save a lot of money. The other things that the VFDs offer is slow, nice startups on the system. You're not engaging full line power to motors where belts are squealing, contactors chattering, things like that. So it's a lot easier on the system. Your maintenance costs overall should be less with those types of systems. The other thing, I guess the other thing we want to talk about is curing cycles. And what we have is we realize that there's a savings based on the curing cycles, that you could use force dry, which basically means that we're using 100% outside air to paint, and then in the curing mode we turn that speed down to half, and we crank up the temperature, so we're basically curing at half the flow rate we would at paint. And that saves energy because you're not using the full volume.
I think we do get questions a lot of times on why we go half speed for flow, because typically when you're curing, you want transfer into the part. You want the heat to get to the part. You want to move enough heat so that the part heats up quickly. But when you go force dry, like Brian said, we can get a higher temperature rise out of the air makeup unit without oversizing the unit itself. Because if you try to cure at full speed, you're going to have a lot of BTUs pumping in, and most of the time you're not going to be using that. So your system is going to be operating really efficiently because you have a way oversized burner. Mm-hmm. So you don't want to go that route. But yeah, absolutely. If we go to the force dry route, move half the air, we can get that temperature from the same unit, and we save a lot of money on the back end, because cure mode is your higher temperature. At the higher temperature, you're exhausting more energy out the stack, and it's a huge savings if we can cut that flow down.
Right. So the other option on curing is recirculation, and this is where basically we allow the air in the booth to recirculate past the heater and allow curing at that full velocity, near the full velocity that paint would be. And going with what Andy said, the air movement in the booth being that much greater helps with drying the part. But the other large thing it does is it reuses that heated air, so you're not heating as much of a volume of air, maybe 15% or 20% of the air you would heat during painting. So that's a considerable energy saver. Even compared to force dry, it's typically 30 to 40% energy savings by having a recirculation cure mode versus a force dry. This chart illustrates the energy use for two different climates, one in Eau Claire versus Dallas, Texas, Eau Claire being the left and Dallas on the right, for different types of curing systems. This is based on a 12,000 CFM system, operating 4 hours a day for painting and 4 hours of curing per day, 5 days a week for a year. So you can see that operating costs can vary as much as greater than $16,000 a year to down to $5,000 a year, depending on the type of system that's incorporated. As we move further from left to right on this, the system is more complex but more energy efficient. So these are, we have controls that are incorporated to get you the energy savings you need. So if you have a process that has a lot of runtime, we can evaluate the energy and develop a design that's going to save energy. So with that, we in engineering like to work on those special projects and so forth. I mean, we get involved with the specialty projects, reviewing specifics of the customer, what they're looking for, and if we can offer something, it would be the ability to take a look at energy savings or the energy costs, estimated energy costs for end users, so we can design a system to be most energy efficient. So with that, this is the information that we would be given from an end user to evaluate the energy use and look at energy efficient options for the customer. So we need the location, their energy costs in regards to electricity and heating, paint and cure mode settings as far as temperature is concerned, how many hours a day are they painting, how many hours a day are they curing, and then of the painting, how many hours a day when it's in paint mode are they not actively painting. So those are all good information that we can use to develop a system that's going to be energy efficient. And then, like we talked about with the economy mode, is having an understanding of your process to, with some input, how many minutes or how many hours per day would this booth could this booth sit in an economy mode versus paint mode. And with those inputs, we can help design a system that'll be efficient for you and meet your requirements.
Yeah, we can take this, we can put together a balance. I mean, there's obviously a number of solutions that are going to work for you. So we can show you, with this, we can show you what your upfront costs are going to be versus your cost savings down the road. And you'll get essentially a payback time for going with a recirculation type booth. So yeah, we added one chart kind of at the end here. That's kind of my decision to throw it on here. So hopefully I don't confuse anybody with this, but this is a psychometric chart. Essentially what we do with these charts is we take your location. This is specific to Wichita, Kansas here. You'll have your electricity and heating inputs on that you'll give to us, and then you'll give us these set points. So these set points, especially the paint one, will come onto this chart and it'll show us exactly where you want to operate your booth. We get data from ASHRAE and we get data from TMY. TMY is like a data set from all kinds of different remote stations across the world, actually. And they take an average representative year for your location, and you can plot hourly data. So we can get down to the hours of operation that you actually run your booth, and we can tell you what the temperatures on average are during those hours during that time of the year. So if we chart all this out on this graph, and we would do this at Global for you, we won't expect you to have to interpret this, but we can tell you exactly where you need to operate your booth. We can show you how many days you would be, or even how many hours you might be outside of your target temperature window. And you can make some decisions on what you want to size your equipment at, maybe what times of the year you may experience issues, or even times of the day. So it can help you cut some upfront costs off your equipment. It can also give you an idea of where your booth might be more energy efficient, or how to design your booth to be a little more energy efficient. So this just helps us give you options, and then you can make some decisions on where you want to go.
Where all of these benefits really add up are for those high production users, where they have lots of hours. Obviously, every hour you're operating, that costs money. And if you have a production line, high capacity production line, etc. All of these items are things that we need to incorporate in the design to make it most efficient for you.
Yeah, absolutely. It's going to be very different for some of our industrial customers maybe versus some of our auto refinish who might be using a system like we have here in our Center for Excellence, where you have very specific equipment doing very specific jobs, and you want the paint booth to be in a specific mode all the time. Where industrial might be using the same booth for multiple applications, where it's only in paint for a very small fraction of the day. Our roll-through systems are going to have a paint booth that's pretty much in spray mode for a majority of its usage. So it's highly dependent on what your process is. So the more information we get on the process, the better we can help you to design your system to be as efficient as possible.
Yeah, and like Andy said, we would take the weather data for your location, incorporate that into our analysis, and be able to put together reports so that you can make a conscious decision on which way works.
And you know, one thing we didn't cover here, and we're sitting in a Revo booth, but we haven't talked about Revo. It's very specific to auto refinish product lines currently, but that is another energy efficiency gain by going with something that can cure much faster. It is electric, not gas, but by using a much faster cycle, you're going to use less electricity, and again, you're going to get a payback period that's, in most cases, I think, pretty attractive for customers.
Thank you for watching. If you guys have any questions, please reach out to us or go to our website at globalfinishing.com. Thank you.